Alright, in this video we'll be looking at the normal approximation to the Poisson distribution. So if you've got a Poisson distribution with lambda which is large enough such that lambda is greater than 15, then we can use a normal approximation. So if you've got x follows a Poisson distribution with lambda and lambda is greater than 15, then we can approximate a normal distribution and say that x follows a normal distribution with mean lambda and variance lambda, because remember, under a Poisson distribution, lambda is both mean and variance. Alright, so let's look at a few example questions. Drops of water fall randomly from a leaking tap at a constant average rate of 5.2 per minute. Let's skip part A. What we're interested in is part B. Use a suitable approximating distribution to find the probability that at least 650 drops fall during a randomly chosen 2-hour period. Alright, so let's define our random variable x as the random variable number of drops that fall during 2-hour period. And so x is going to follow a Poisson distribution, and lambda here we're given 5.2 per minute, so we've got a 2-hour period, so 2 hours is 120 minutes, so we can say 120 multiplied by 5.2, since this is per minute, 5.2 per minute, so 120 multiplied by 5.2 to get per 2 hours. So 120 multiplied by 5.2, that gives us 624. So it means our lambda is 624. And we've been told to use a suitable approximating distribution. So here lambda is equal to 624, which is greater than 15. So we can use a normal approximation. So it means that x follows a normal distribution with mean lambda and variance lambda. So x follows a normal distribution. Mean is going to be 624, variance will be 624. And we're finding the probability that at least 650 drops fall. So the probability that x is greater than or equal to 650. That's what at least means. But we know that our Poisson distribution is a discrete, and this probability here was defined under discrete conditions, and now we have approximated to a normal distribution, which is a continuous distribution. So 650 under a continuous distribution means any value from 649.5 up to 650.5. So we want greater than or equal to 650, so we want to include 650, and we're going towards the left. So we take the smallest value represented by 650, which is the 649.5, and we're moving to the right. So it's going to be the probability that x is greater than 649.5. And at this point we can standardize. So the probability that z is greater than 649.5 minus our mean, which is 624, divided by our standard deviation, so square root of 624. And so the probability that z is greater than, let's punch this into the calculator, that's 649.5 minus 624 divided by the square root of 624, and that gives us 1.021, correct to 3 decimal places. So this would be 1 minus phi of 1.021. Let's read off the value of phi of 1.021 from our normal distribution tables. That's 0.8463. So this here simplifies to be, that's 1 minus 0.8463, so it simplifies to be 0.15, it's 0.1537, which to three significant figures is 0.154, and that would be our final answer. Alright, so let's look at another example. Here we're given that the number of inquiries received per day at a customer service desk has a Poisson distribution with mean 45.2. If more than 60 inquiries are received in a day, the customer service desk cannot deal with them all. Use a suitable approximating distribution to find the probability that on a randomly chosen day, the customer service desk cannot deal with all the inquiries that are received. Alright, so let's define our random variable x. Let x be RV, is the number of inquiries received per day. Number of inquiries received per day. And so this means that x follows a Poisson distribution, and they've given us mean as 45.2, and they want us to use a suitable approximating distribution. So lambda is equal to 45.2, which is greater than 15. So it means we can use a normal approximation to the Poisson distribution. So x follows a normal distribution with mean lambda and variance lambda. So x follows a normal distribution with mean 45.2 and variance 45.2. And we want to find the probability that the customer service desk cannot deal with all the inquiries received. So when can they not deal with all the inquiries received? If they get more than 60 inquiries per day. So we want to find the probability that x is greater than 60. Because if x is greater than 60, then the customer service desk cannot deal with all the inquiries. Alright, remember your Poisson distribution is discrete. We've approximated to a normal distribution, which is a continuous distribution. So we have to carry out continuity correction. 60 represents values from 59.5 all the way up to 60.5. And we want greater than 60, so we don't want to include 60. So this will be greater than 60.5. So the probability that x is greater than 60.5. So let's standardize. That's the probability that z is greater than 60.5 minus our mean, which is 45.2, divided by our standard deviation, that's the square root of 45.2. And let's punch this into the calculator. That's 60.5 minus 45.2 over the square root of 45.2, and so this gives us 2.276. correct to 3 decimal places. We can write this as 1 minus phi of 2.276. So this is 1 minus, read off the value of phi of 2.276 from the normal distribution tables, and you get 0.9886. So 1 minus 0.9886 gives us that's 0.0114, and this will be our final answer. So this is how you use the normal approximation to the Poisson distribution.